Right. Okay. So we're almost there. So let me go ahead and start. I would like to welcome everybody back to the SPIN+X SPICE online seminars. As usually, this is a Zoom webinar format, meaning that the attendees can just listen to the talk at the moment with a speaker that at the time seen on the side of the screen. But you can ask questions, a Q&A on the, as you know, Oliver just said hello, and the same with her. And every attendee should be able to see the questions and even comment on the questions if you want to interact as well during the time, but please do it politely. Anybody that abuses the system will be kicked out and unfortunately banned from SPICE from now on. The talks are usually on Wednesdays at 3 p.m. We've been now regularly holding them, and we hope to continue that through the fall as well, as much as possible. And then we actually look forward also next week. Stefan Blugel will be giving a talk that will post shortly the abstract from Beyond Heisenberg Solids from Multispins Interactions to Novel Chiral Particles, and Hideo Ono following that. And we will try to keep on, but feel free to suggest the speakers as well to us as things progress. Today is a very nice to introduce the speaker. Rembert Duine is a full professor in Utrecht University, had his PhD in Utrecht, but also we overlapped together as young punks as in the Alan McDonald's team in Texas. He is very well known in Spintronics community with emphasis on magnetic insulators now and other spin physics and long interactions, but has also a strong background on Bose-Einstein condensates and atomic systems. And among some of his awards, he's been well funded, with particularly the starting grant and consolidator, and I expect that in a few years they advance as well. So with that, I'm going to stop my introduction, and I'm going to ask Rembert to please go ahead and share your thing, yeah, and go ahead and start your talk whenever you wish.
Okay, 1 second. Okay, do you hear me okay, Jairo?
Yeah, very well, thank you.
Thank you very much. Let me also make use of a laser pointer. Yeah, so first of all, thanks to Jairo and the other members of the other organizers of this nice seminar series to have invited me here for the talk. It's also nice that these talks are actually being recorded. So often I watch these talks from my shed in the morning while sitting on my home trainer bicycle. So it's a really wonderful addition during this pandemic times. So I'm affiliated mostly with Utrecht University, but also have appointments at Eindhoven University of Technology, which is another university in the Netherlands, 1 hour away from Utrecht, and with Ada Bratas' Q-Spin Center in Norway. And so today I will talk about phonon spin, and in particular about how you can use phonon spin to get long-range spin transport. But I also talk halfway through the talk about, let's say, some fundamental results from the fact that phonons have spin. And so most of the things that I'll be talking about you can read in these two very recently published papers. So just to set the stage, what is the, let's say, the grander goal of what I'm going to be talking about? So, and the grander goal is to achieve dissipationless transport of something, and this something in my case will be spin. And so this is motivated by, let's say, replacing replacing superconductors as another carrier of dissipationless transport, in this case charge. So if you have a superconductor and sandwich it between two leads, then the dissipationless transport will signal itself as, let's say, the current, in this case charge current, through this device from one lead to the other lead will be proportional to the bias for low bias divided by resistance, and then the resistance is independent of the length of this superconductor. So it's not ohmic, namely not increasing with length, but it's a dissipationless charge transport, so independent of the length. Now, in principle, this would be wonderful for applications that would like to save energy, for which it's important to save energy, to reduce energy consumptions. But unfortunately, all superconductors we know occur at temperatures below room temperature. And therefore, it might be promising to look rather to look into charge, to look into spin as a possible quantity that's carried in a dissipationless way, and that just by changing the word, going from superconductor, that would mean that we're looking for something that's called a spin superfluid, where you could imagine having this spin superfluid, which is something I'll not talk about much, but let's imagine that there exists a material or that has the property that it's able to transport spin in a dissipationless way. So if this exists, then I could imagine sandwiching it between two leads and transporting spin dissipationless without dissipation. Of course, the entire phenomenology would need to be revisited. So how this exactly would manifest itself is to a large extent still unknown, especially experimentally. But because spin is usually associated with magnetism and exchange interaction, it might have a more promising, it might be more promising for achieving this above room temperature, for the simple reason that exchange interactions are typically strong. For example, much stronger than the electron-phonon interaction that underlies conventional superconductivity. So the prospect here would be that this might actually be possible above room temperature. Okay, so this is kind of the grander goal. So what are but before we kind of dive into this more specifically, so what are the kind of steps that have already been made in spin transport? I'm going to reiterate these just to get everybody on the same page. So the first, let's say, step in Spintronics historically was undertaken by looking at spin transport in metals or semiconductors. So here is a typical device, and I'm focusing here on non-local spin transport. Non-local meaning that the injection part and the detection part are kind of distinct. So it's a 4-terminal device, 1, 2, 3, 4 terminals rather than 2. And so how does this work? So the idea here is that you take a, let's say, non-magnetic metal or non-magnetic semiconductor. You put a magnetic metal here, let's say a conventional metal here, and you drive a current. And the idea is that the spin polarized current, let's say the current that gets through this injector, metallic ferromagnetic injector, is injected here. And so the charge current injection is accompanied by a spin accumulation. However, the charge current goes to the left, but the spin might actually diffuse from this injector E2 to some other detector E3. And then it's picked up again in a non-local way. So in this non-local geometry, it's possible to measure spin transport properties of metals and semiconductors that are not magnetic, so not spin polarized in equilibrium, to measure them without the accompanying charge transport. And so the idea is that the spin diffuses, but spin can also relax. It's not a conserved quantity, as we theorists like to call it. So there can be spin flip scattering events, and there can be a decay of the spin density throughout this structure. And that's usually described in terms of an electron spin accumulation. So this is a spin chemical potential that gives that indicates the amount of out of equilibrium spin polarization, and this typically decays with some length scale. Now, if you then measure the non-local resistance, so that would be the voltage that you measure here divided by the current that you drive here to inject the spins, you would this define a non-local resistance. You would find that this non-local resistance decays exponentially for large distances with the distance between, let's say, injector and detector. So here's now a typical device where this is done on a graphene flake. And I mention here graphene because the most modern experiments are done typically on graphene, because it's one of the most recent materials on which this was done, or at least most recent class of materials, these 2D materials. And it also has very long spin relaxation length. So if you look at the spin diffusion length for, let's say, metals and semiconductors, graphene would be at the upper end with micrometers or maybe even tens of micrometers. Whereas, let's say, conventional metals, copper would be in the hundreds of nanometers. And if you have strong spin relaxation, for example, engendered by strong spin orbit coupling, heavy metals, then you would really go to a regime where this would be, this diffusion length would be comparable to the mean free path, and perhaps even equations like this are not valid anymore. Okay, so this is kind of the setup for metals and semiconductors. So we have a reservoir for spin which is made by this non-local way of injecting spin. Spin diffuses to some detector. And these are kind of the properties. You describe it with a spin accumulation, there's a non-local resistance, and there's some spin diffusion length, which is typically, let's say, so let's take copper as the paradigmatic example. This would be in the hundreds of nanometers. Now then, around 5 years ago, there was a, let's say, quote unquote paradigm shift where this was done not anymore with, was achieved not anymore with metals, but also with magnetic insulators. And so let's first focus on this device on the right. So the idea here is that it's basically the same, but the setup is slightly different. So here we again have a spin conductor, which in this case is this magnetic insulator, this black film here, magnetic insulator yttrium iron garnet, YIG. And then as an injector, there's a platinum strip on top of this magnetic insulator through which a current is driven. And there's an adjacent platinum strip, this vertical line here, across which a voltage is measured. And these are not contacted electrically in any way because they are just contacting both to the magnetic insulator. And the idea of this experiment is now that this injector, so this is the actual device, and this is now a schematic of what's going on. So the idea is here that the injector, which is in the schematic, is this strip here. The injector is made of platinum, has strong spin-orbit coupling and a large spin-hole effect. So this charge current, which is driven here through the platinum, so this is not going through the YIG, that would not be possible. It sets up a spin current transverse to it, but this spin current can actually be injected in a magnetic insulator and is carried in the magnetic insulator in the forms of spin waves, fluctuation in the magnetization, spin waves or magnons, say. And these magnons travel from injector to detector, and then at the other interface between insulator and platinum, the reverse process happens, and that sets up a voltage. Okay, so in this case, the essential quantity is not the electron spin accumulation, but is the magnon spin accumulation, which also decays exponentially with a characteristic length scale, which is the magnon spin diffusion length. You can also define a non-local resistance in this case. So it would be, let's say, the voltage that you pick up here divided by the current that you inject here. And this would be decaying exponentially with the distance between injector and detector. By the way, these strips are so long here just to be able to pick up measurable signals. So this would decay exponentially with the distance between injector and detector. And this would be a measure for the spin diffusion length. And now this first experiment that was done in a group of Bart van Wees immediately showed, without any optimization or any particular fine-tuning or so, a spin diffusion length of that's already tens of micrometers. So immediately being on par with the best let's say with the best electronic spin conductor graphene at room temperature for yttrium iron garnet. Now, in the meantime, this experiment has been reproduced and done in various different ways, in particular also on antiferromagnet. This was done 2 years ago by the group of Matthias Kloy. Also showing long decay lengths of these, let's say long compared to electronic spin currents, long decay lengths for these magnetic insulator, either ferro or antiferromagnetic. And so again, to rephrase the general view and to already give away what this talk will be about. So in both experiments, both electronic and magnonic, there was a reservoir of angular momentum, spin angular momentum, some incoherent carrier of the angular momentum transport. So in one case, it was spin polarized electrons. In the other case, it was magnons, spin fluctuations in the magnetic insulators, and then some detector reservoir. The case of electrons, hundreds of nanometers. The case of magnons, tens of micrometers. And in this talk, I will talk about replacing this intermediate carrier of angular momentum by an ordinary insulator. So an insulator that does not have magnetic order, it doesn't have electrons or magnons, but it has phonons. I will try to show that these phonons can actually also lead to long-range transport, spin transport, and have a decay length that's in the order of millimeters even. But that will be towards the end of my talk that I'll go through this example. So before diving into a little bit more details, so let me introduce my collaborators. So most of the work that I'll be talking about was done by Andreas Rikriegel, who was a postdoc at the time in Utrecht University and has now moved to Frankfurt University earlier this year. He worked together with Simon Strijp, who was a postdoc at the time in Delft University, working with Gerrit Bauer. Simon is now in Uppsala. Unfortunately, his web presence is so low that I could not find a picture of him. And then Gerrit Bauer was together with me collaborating with these two junior people who actually did all of the work. And Gerrit, I put a picture here, but most of you will know him, of course. And most of this work was actually financed by a FOM program on Magnon Spintronics and by the consolidated grant that I got a while ago. So I'll first introduce, so to understand how phonons can transport spin, I first have to introduce the concept of phonon spin. And then I'll go into an historic, well, let's say I'll go into the Einstein-de Haas effect, or rather the Einstein-de Haas like effect. So I'll discuss a couple of examples from which it's already clear that the phonon spin is important. And that's then a motivation to understand if you can also achieve long-range phonon spin currents with just phonons rather than also including magnons, for example. Okay, so first let me dive into phonon spin. So phonon spin was actually proposed already a long time ago, but largely forgotten. So thanks to Simon Strijp, one of the collaborators, we became aware, well, he actually dug out a very old paper, Russian paper, which apparently is the first to introduce phonon spin. And this was followed up, although I think this paper by Levin was not aware of this earlier work. 1 year later. And then it was silent for a long time until Shan Liu and Garanin and Chudnovsky kind of reintroduced phonon spin again. And then it was kind of picked up by the Spintronics community after that. So there's a nice paper by Nakano and Kono on the definition of what phonon spin is precisely. If you have questions about that later, I'm happy to answer them. It's a little bit technical for now. And Simon, together with Ajay Kester and Bauer, proposed enhanced damping due to phonon spin pumping. And this paper, for example, looks at various different crystals and how to enlarge the phonon spin angular momentum. So basically what the idea is of phonon spin is that circularly polarized phonons, so phonons typically come in 3 polarizations, 2 transverse, 1 longitudinal, and by building superposition of superpositions of transverse polarized phonons, so where the atoms, let's say, vibrate orthogonally to the propagation direction of the phonons, by building superpositions of that where the atoms vibrate on a circle, to say it in a, let's say, quote-unquote kindergarten way, kind of way, you can actually give the phonons spin angular momentum or angular momentum. And this is very much similar to the angular momentum of photons of the electromagnetic field. Now, this is a picture taken from the paper by Garanin and Chudnovsky, and they were first to kind of in a pedagogical way explain how you can, in principle, if you have a mechanical object, how you can disentangle the contributions to the angular momentum of the mechanical motion of this object into a global rotation, which is sketched here, where the entire body rotates, and then disentangle that from the phonon spin, where the atoms actually vibrate, but in this circularly polarized way, but which does not lead to a global rotation of the entire mechanical body. So this is very much in the same way as decomposing the translation of an object into, let's say, a 0 wave number mode, so just uniform translation, and then vibrations on top of that. So this is doing the same thing, but not for translation, but for rotation. Okay, so this is how phonons can have spin, at least theoretically, but now is the question, does this also exist in an experiment? And the answer was yes, as was shown in a beautiful experiment by the group of Resende. And so what they showed was that if you convert a magnon into a phonon, that actually the phonon that you end up with has a spin of h bar, just like the magnon you started out with. So how does this experiment work? So what they use is a film of YIG on top of GGG. This is a very, let's say, conventional quote-unquote combination. And what they do is they excite with a microwave. They excite a magnon. So with a pulsar, they can excite a wave packet of spin fluctuation. So a spin wave, a magnon that travels from left to right, and they can measure this on the other side. And they will do this with a Brillouin light scattering. But now in this particular system, for this geometry, for this direction of field, there's an avoided crossing between the magnon mode, which is this blue mode here, which is this blue mode here, which is parabolic for large wavelength and has this deviation due to dipolar interaction for short wavelength. So this is the magnon branch. This magnon branch crosses with a phonon, with the transverse polarized acoustic phonons, which is this branch here. And they form, because of magnetoelastic coupling, they form an avoided crossing here, right here at this point. However, the location of the avoided crossing is dependent on where what the magnetic field is, because the magnons are pushed up or down by increasing or decreasing the magnetic field. So in this avoided crossing now, on the very left here, we're dealing with pure magnons. On the very right here, we're dealing with also with pure magnons. Here with phonons, but right here we have a magnon polaron or magnetoelastic boson or magnetoelastic waves. That's a superposition of a phonon and a magnon. And now, because where this crossing is depends on what the field is, by making a field gradient, you can now convert a magnon by adiabatically moving it. If it adiabatically moves along this trajectory, you can change a magnon into a phonon. And that's basically what they do in the experiment. So they apply a field gradient across the sample, and they, let's say, they pump the system at this particular, or they excite the system at this particular energy. And then on the very left of the sample, that means they excite a magnon. But then as this magnon or its wave packet travels from left to right, it goes closer to this avoided crossing and changes its character from being pure magnon into being pure phonon. And then on the right-hand side, they can measure the spin polarization of this phonon by Brillouin light scattering. So the idea is again sketched here. So they excite a magnon on the left, but because of the field gradient, it's converted into a phonon, and then they measure the phonon polarization. And here are angular plots of this phonon polarization of the BLS measurements. Now, I'm not an expert on this, but apparently from these angular plots, you can infer that the phonon has also a spin that is measured, also has a spin h bar, because the magnon that you started out with also has a spin of approximately h bar. So if it's really a circularly polarized magnon, if there's no anisotropy, it would be purely h bar, but because of dipolar effects, anisotropy effect, it may be slightly different from having a spin of h bar. But most of the spin is conserved in this magnon-phonon conversion process. Okay, so this experimentally, from what I understand of it, establishes phonon spin. Okay, so that's how phonon spin comes about. It's made up by creating circularly polarized phonons. And so one of the questions we had, and this is also always indicated actually if you read papers about phonon spin, especially the papers by Xianyu and Dimagaranen, is what now is the role of phonons in the Einstein-de Haas effect, or in Einstein-de Haas-like effects. So what do I mean? First, what do I mean actually with Einstein-de Haas effect or Einstein-de Haas-like effect? So the traditional Einstein-de Haas effect is the following: if you have a freely, let's say, a free mechanical body that can be magnetic in principle, so that has spins. For example, a body that's suspended on a very thin wire and can rotate freely about this wire. If you apply an external field to magnetize this system, eventually this body will start rotating, right? Because the angular momentum that's stored in these spins will be oriented, but this angular momentum has to come from somewhere because of conservation of angular momentum, because the field is pointing in the z direction. So throughout this process, angular momentum has to be conserved. So this angular momentum has to come from somewhere, and this has to come from the lattice. And ultimately, the lattice is coupled to global rotation. So that's why you see this global rotation. And so there's a very old experiment. It was originally done to establish that magnetization has to do something with angular momentum. was established to measure the gyromagnetic ratio, which apparently was done wrong. I won't go into that, but has recently been revived in the context of a field that's called spin mechanics. For example, there are some modern experiments where they use this effect, or rather the reverse, so the magnetization that you get if you rotate a solid body, the Barnett effect. So they measure an angular momentum compensation point of certain magnetic alloys by the Barnett effect, so by rotating a body. There's also a nice experiment for the group of Saito on what they dubbed the spin-Seebeck mechanical force, where they show that the decay of a magnon spin current leads to, let's say, wobbling of a cantilever object. And so these are all kind of what I mean Einstein-de Haas-like effects, where you are interested in studying the coupling between the rotation of a mechanical body, of a magnetic mechanical body, how it couples to the magnetization. Now, there are also some recent theories. So, for example, there's a nice classical theory from the group of Novak, where they solve stochastic Landau-Lifshitz-Gilbert equation couples to stochastic equations for the position of the atoms and apply it to studying the Einstein-de Haas effect. There's also a recent paper motivated in part by experiments on ultrafast magnetization dynamics. So there's some recent activity on let's say, Einstein-de Haas-like effects. So why would you actually consider phonon spin in the Einstein-de Haas effect? And this is actually shown by a very nice argument due to Simon's stripe. So if you look at conservation of angular momentum, so if you imagine that all the angular momentum goes into the solid rotation, then this actually kind of could work out. So the angular momentum in the magnetic system is the saturation magnetization times the volume divided by the gyromagnetic ratio. If you put this equal to the moment of inertia times the rotation frequency, you get that the rotation frequency scales like the volume to the minus 2/3. So it's very small for large bodies, for microscopic bodies, because the moment of inertia scales like the volume to the 5/3. So this could work out, and then you have a very slowly rotating solid body. If you have microscopic system, and this is also what you see in experiments. So these rotations are, you can see them with the naked eye in the classic Einstein-de Haas effect. So this could work out the conservation of angular momentum. You don't need anything else there in principle. However, if you look simultaneously at conservation of energy, which should also be conserved in the experiment, this doesn't work out because the magnetic energy would be the Zeeman energy in the external field. And this is much, much larger than the energy that you get in the that's stored in the rotation, the solid rotation of the body. Again, because the moment of inertia scales like the volume to the 5/3, so this actually becomes very small for macroscopic bodies. So the amount of energy that you can store in the solid body rotation is way too small to be able to absorb all the magnetic energy that changes in this magnetization process. So you need something else. And this something else can only be the lattice vibrations. And then you also need to consider, so the phonons, but then you also need to consider the spin of the phonons. Okay, so we set about trying to formulate a microscopic theory of these type of effects, where you determine what the coupling is between the spins, the phonons, and the global rotation of a microscopic magnetic body, magnetic insulator, say. And this is actually a very, very difficult type of theory. So I will not say much about the precise equation and so on. I just want to sketch how it works. So what we, and this is mostly Andreas's hard work and talent that went into making this a success. So basically what the starting point of our theory was a fully rotation invariant Hamiltonian for a magnetic insulator. So really a free, let's say, magnetic insulator, microscopic body that's allowed to mechanically move, so to rotate, but it also has spins, so magnetization, spin waves or magnons. And then the first thing you should do is to split this mechanical motion into a global rotation and translations plus phonons. Okay, so if you've done that, and how to do this, this is known, let's say, in the literature of molecular dynamics, but not so well known in the context of this Einstein-de Haas effect. macroscopic Einstein-de Haas effect. So once you've done that, you get a couple Heisenberg equation of motion for the spins, the lattice, and the global rotations, ignoring the translations for the moment. And then, so these are too complicated to solve, but then you can reformulate these Heisenberg equations into a quantum kinetic theory for magnons coupled to phonons and their spin. So magnons and spin, phonons have now also a spin, coupled to magnetization dynamics and the global rotation. Now, this is still too complicated to solve. And then we solve this quantum kinetic theory. So these are Boltzmann-like equations, say, in terms of phonon temperatures and the phonon drift velocity. So this parameterizes the out of equilibrium situation for the phonons. So there's a change of temperature of the transverse phonons, a change of temperature of the longitudinal phonons. So these are weakly coupled. You should treat them separately. And a phonon drift velocity, which parameterizes the phonon spin and the phonon spin current. And then there's a magnon temperature and a magnon chemical potential. So this magnon temperature captures the change in energy of the magnons. This captures the change in spin of the magnons, is magnon chemical potential that I talked about earlier. And from this, you can compute the change in spin density, phonon spin density, and the global rotation. So what I'll show, so this is a very involved theory. If you're interested in this, then please go read this paper. Or perhaps I should say study this paper, because I also regularly have to study it again. And then you can compute by solving equations for the phonon temperatures, etc. You can compute the change in the spin density in the magnetic system, the change in the phonon spin density, and the change in the global rotation, so the rotation frequency, as a function of time after some given initial condition. Okay, so the next slide, I will discuss briefly some results that we got out of this theory. And so here's the first result. So this is, again, let's say the setup. We have a cylinder of magnetic insulator now, because it's rotation invariant. The rotation frequency always refers to a rotation around this, let's say, z-axis, magnetic field along this axis, and then there can be mechanical angular momentum in the phonons and global rotation, and there can be spin angular momentum in the magnetic system. And the first initial condition that we consider is that we, let's say, we imagine that this system is brought out of equilibrium by a laser pulse that only heats up the phonon system. So it couples to the phonon system. So this injects energy in the phonon system, and the angular momentum is conserved in this entire process. So what you see here is, for example, the temperature change in the the temperature change in the magnon and phonon system. So you see that the two phonon temperatures are initially large. So we model this by just putting them, let's say, a fraction of a degree higher than the initial temperature. And then the magnon temperature is kept constant in first instance, but it quickly starts equilibrating with first with the temperature of the longitudinal phonons, and then with the temperature of the transverse phonons, until eventually all the temperatures equilibrate to some finite value that's higher than the initial value, because we have injected energy into the system. So at the level of the energetics, this is pretty much what you would expect. However, because the temperature of the magnon system increases, the amount of magnons will increase. However, angular momentum is conserved, so this the amount of magnons will increase. But this angular momentum that's stored in the magnons has to come from somewhere, and it can only come from the phonons and from the global rotation. So here you see in this blue line the increase in angular momentum, increase in spin density in the magnetic system, and you see basically that the global rotation tracks this change in this increase in angular momentum in the magnetic system, and the phonon system also tracks it. However, the total amount of angular momentum in the phonons is one order of magnitude smaller than for the magnetic system. So for this particular initial condition, you can pretty much forget about, or let's say neglect phonon spin. Now, if you look at at magnon chemical potential and at phonon drift velocities, so here you see the magnon chemical potential here. So you see the magnon chemical potential shoot up to accommodate the increase in magnons here. And so also the phonon spin current goes up, which is this dashed line here. Now this increase of this increase of magnal chemical potential was actually not in this particular setup, but in a similar scenario was also used to achieve Bose-Einstein condensation. So if you very rapidly heat up a magnetic insulator and then let it cool down quicker quicker than the spins can relax, then you're able to achieve magnon Bose-Einstein condensation, and this was done in this paper here. Okay, so this is basically the defining of this is pretty much like you expected. You heat up the system, you get more magnons, so more angular momentum in the spin system. This has to come from somewhere, and that's why the magnetic insulator starts rotating. A phonon spin is not so large in this particular case. However, if you look at a different type of setup, so these are similar plots, but now for a different type of, let's say, initial condition, different type of experiment. So we have the same system, but rather than heating this up, we imagine injecting magnons by parallel pumping. Okay, so this is basically means that you vary the field in amplitude, and if you then have dipolar effects, you can actually inject magnons. However, this process, since it's you vary the field parallel to the z-axis, you conserve angular momentum throughout the entire process. So basically, we model this parallel pumping by setting the initial magnon temperature and magnon chemical potential to be larger and non-zero. So that's what you see here. The magnon temperature, this blue curve, is large, and then it quickly equilibrates with the phonon temperature. Here you see the magnon chemical potential also being large, and then it eventually decays to zero. And now something peculiar happens. So first of all, with this setup, so if you inject spin in the magnon system, then the total contribution of the phonon spin is comparable to the magnon spin. So here so this is the spin density in the magnon system is this blue curve, and the phonon spin is this red curve, and you see that at intermediate times they are comparable. Of course, eventually, since phonon spin is really an out of equilibrium concept, it should always go to zero eventually, whereas the magnon spin survives at some point at finite temperature. But at intermediate times, so right after you inject the magnons, you see that the phonon and magnon spin are very much comparable in magnitude. And moreover, something peculiar happens to the global rotation of this body. Namely, it starts rotating first with one sense of rotation and then reverses its sense of rotation and then reverse back again until eventually it rotates in the way that you would expect from angular momentum conservation. But the fact that these phonons are so dominant in the intermediate phase means that because of total angular momentum conservation, the body starts rotating oppositely from what you expect. Okay, so the bottom line is, if you would do this Einstein-de Haas-like experiments, you would have a free magnetic body that's allowed to rotate freely, and you would do parallel pumping. You might see this very atypical, anomalous change in sense of rotation right after you inject the magnons. Okay, so this kind of shows that phonon spin in these Einstein-de Haas-like effects and in general is not negligible and can be as large as magnon spin. So let me skip this example. So this was the first part. So if you didn't understand anything of this first part, don't worry. The only thing that you should take away of this application of phonon spin, or figuring out what it does to the Einstein-de Haas effect, should be that the phonon spin is important. So we cannot easily ignore it. So that's an important conclusion. But now, the next question is, what can we actually do with these phonons and their spin? And that will be the final part of the talk. And so basically we considered this setup here. So this is very much like the earlier setups that I showed for semiconductors and metals, but now it's so it also has some reservoir, let's say an injector, a detector, and then something in between. But rather than having a metal or semiconductor, something with electrons, or a magnetic insulator, something with magnons, I now have a non-magnetic insulator in between. So this could be GGG, and for most of the results that I'll explain, this will actually be, we take the parameters of GGG, the usual substrate for YIG. And so this just has phonons, basically. And then the reservoirs are now actually magnets that are brought out of equilibrium. So this could be, for example, so these are magnetic insulators. So we imagine them to be magnetic insulators, for example, YIG. And we take most of the time the parameters of YIG. So magnetic insulator where the spin, the magnons are being introduced, for example, by an additional platinum spin injector that injects spin into a magnetic insulator. That's not so important. The only thing what's important is that these magnetic insulators, they should act like angular momentum reservoirs that are being pumped. So they are out of equilibrium. They have a magnon chemical potential, and these magnon chemical potentials could be different. Okay, so we have magnetic reservoirs that may inject angular momentum into the intermediate phonon system here. And now what we get is we get actually spin transfer due to the magnon-phonon interaction. So due to ordinary magnetoelastic interactions that occur in the magnetic insulator. So in this magnetic insulator, you get magnetoelastic interactions between magnons and phonons. At the interface, the phonons couple. And then here you get the reverse process where the phonon spin, or some signal at least, will be converted back into a magnetic signal. Excuse me. Now, how do we model this? Again, I will not say much about the precise details. You can, again, read it in this paper here. But we use, let's say, conventional magnetoelastic, so conventional equations for the magnetization, so the stochastic Landau-Lifshitz-Gilbert equation, and similar equations for the displacement of the lattice. But both of these equations are, we use finite temperature generalizations. So we, by introducing stochastic forces, and that introduces then a temperature and is able to describe then as a result this incoherent transport. So not only the single wave, say, but also how they are occupied with thermal occupations. Okay, so what do we then get? And again, the details are in this article here. So first of all, so here's again the setup just for reference. So the first thing you can calculate is actually this total spin current that is carried from left to right in this setup. So if you do that, if you grind through the formalism, then you got a Landau-Büttiker-like expression of this kind, where you see that the total spin current is an integral over frequency, and some transmission function that depends on frequency, and then a difference of to occupation numbers, which are not Fermi-like factors here, but here we're dealing with bosonic fluctuations, magnons and phonons. So these are Bose functions at different chemical potential, at different magnon spin accumulations. And of course, if there's a difference between this left, the bias of this left reservoir, the spin accumulation, magnon spin accumulation of this left reservoir from this right reservoir, this becomes non-zero and you get a non-zero spin current. So just to give you an idea of what you get, so here's a density plot of this transmission function as a function of length of the non-magnetic system. So this intermediate system has length L, and as a function of frequency. And what you see here are these broadened resonances. So basically this vertical line here is the phonon branch, and these are the magnons in a magnetic insulator. And you get all these resonances, and they basically signal when an entire phonon fits in this entire, when a phonon fits in this entire structure. So that's this resonance condition here. So this is the length, the total length of the system is L plus 2D. Lambda tilde is the wavelength of the phonons in the intermediate system. Lambda is the wavelength of the phonons in the magnetic insulator. So if this is equal to an integer, you get these resonances in the transmission function, because basically a phonon fits in this entire structure. Okay, so this is what you get for the transmission function. And then basically, if you linearize this Landau-Büttiker-like formula, you get kind of an Ohm's law, say, for the spin current. So you get a spin conductivity, which is called sigma here, which times the bias would be the spin current. And if you, so basically, calculating the sigma amounts to taking a thermal average over this transmission function. So these resonances are not as sharp anymore in the spin current, but here's now the density plot of the spin conductivity as a function of the length of the magnetic insulators and the length of the non-magnetic insulator. But you see again these enhancements right as you fulfill this resonance condition. Okay, so is this now long-range spin transport? I've not said anything about that yet, and that's the title of my talk. So to establish the length scale of this, you need to calculate the spin conductivity, which is plotted here on a logarithmic scale, as a function of the length of the non-magnetic insulator, shown here. And this plot is now for YIG and GGG parameters. So we take the known Gilbert damping for YIG, the known, let's say, acoustic quality of GGG. And then you find these blue curves here. And so basically in the beginning, this is an oscillatory signal here. So in the beginning it oscillates. So that's why we're plotting here an envelope of this oscillating signal, but then eventually it becomes a steady decaying signal here, which is fitted well by an exponential decay. And this exponential decay is kind of like the spin relaxation length of the phonons, if you will. And for the parameters of GGG, this decay length would be about 1 millimeter. Okay, so this is already much longer. So this would be much longer than the Magnon spin diffusion length that was measured for YIG, for example, and for hematite in the experiments by Professor Chloe. So this looks very promising. Is there now also a large spin accumulation and spin current? Is the signal not due to something else? So we've also calculated the spin density and the spin current throughout the structure. So here you see the distance. So this is in the left magnetic insulator, the right magnetic insulator, the non-magnetic insulator. And here you see a plot of the spin density of the phonon systems that we get out of our stochastic magnetoelastic equations. And you see very large phonon spin densities that are comparable to Magnon spin densities for typical numbers. And you see also even out of equilibrium large phonon spin currents. And these phonon spin currents and these spin densities are basically set up because of the fact that you drive the Magnon system out of equilibrium. And you see very sharp features here at the interface because the magnetoelastic interaction actually becomes a boundary condition and injects spin right at the interface. So again, these are technical details that we can discuss later if you would like to. So even in equilibrium, there's a phonon spin current. However, only out of equilibrium, it transfers spin from the left to right reservoir, because in equilibrium, equilibrium is the dashed line here, the entire spin current integrates to 0 over the entire structure. Anyway, the bottom line of this result is that the phonon spin and the phonon spin current is large, and I can therefore also mediate these long-range spin currents. Okay, so does this also now occur in experiment? Yes. So there's a very recent experiment by the group of Olivier Klein that was actually posted slightly before we did our theory work. So this experiment is not done in the incoherent regime. So our theory was really looking at incoherent spin transport, where we imagined that we had reservoirs of spin angular momentum that were coupled through a phononic system, a phonon system that mediates spin via the phonon spin that I introduced at the beginning. This is not done in this experiment. In this particular experiment, one looks at the coherent regime because here the system is driven by a ferromagnetic resonance, so by a transverse field. So the idea here is to, the setup is that there are two YIG slabs that are put on both sides of a GGG thicker film. And then as you look for FMR in this system, you see signs of coupling of avoided crossings between the two, that signals coupling of the two resonances, of the two magnets. And that's an indication of phonon spin. And then you see such a, let's say, I forget now whether it's a theoretical plot or experimental plot, but you see these resonances And these are similar to our, for example, to the plot that I showed for the transmission frequency, although there this axis was frequency, not magnetic field. And here there are two ferromagnets, so there are two almost horizontal lines for the phonons in these two ferromagnets. Okay, in any case, this experiment shows coherent coupling between the two ferromagnets across a non-magnetic insulator that's mediated by phonons in this non-magnetic insulator. And so to go to what we propose to do, one would have to, let's say, inject spins in one of these magnetic insulators with, for example, platinum incoherently, and then detect them with a platinum spin detector on the other side. And then the spins would be traveling from left to right via the non-magnetic insulator. Okay, I'm almost at the end of my my talk, so let me just wrap up. So I've talked about, so this was a slide I had at the very beginning. I've talked about how you can get incoherent spin transport in electron system, magnetic systems. And what we've shown theoretically is that phononic systems, so phonon spin, can actually travel over, well, at least we predicted that it's possible to travel over a very long range, longer than the magnetic system, because it's basically limited by acoustic quality. So electrons are limited in their spin transport properties by spin-orbit coupling and disorder or scattering of phonons, say. Magnons are limited by the magnetic quality. So of course, YIG has a very large magnetic quality, but acoustic quality factors can be even larger. Larger. And that's why phonons can transport spin over perhaps even longer distances. Now, of course, I would not believe any of this unless there are experiments to be done. So this coherent phonon transport has been demonstrated, and as I demonstrated by Olivier Klein, as I indicated, I think this is not such a big step away from showing really incoherent spin transport of one spin reservoir to another spin reservoir via phonons. Now, to come back to spin superfluidity, this talk was all about incoherent spin transport by, let's say, particles, single particles. So what about spin superfluidity, which is more like transport of spin by a collective degree of freedom and not a single particle spin transport phenomena? So I just would like to challenge my experimental colleagues that are hopefully in the audience to also do phonon superfluid spin transport in the following way. So this is a picture by from a paper by Sonon, one of the founding fathers of spin superfluidity, who actually shows and argues that if you take a rod and twist both sides of the rod and then glue them together, then this actually is a state that supports a superflow of angular momentum, and so is a how do you call that? A steady state of dissipationless carries a dissipationless flow of angular momentum. So what I would like to challenge my experimentalist colleagues to do is to build, let's say, such a device at the nanoscale where you inject angular momentum on one side from a magnetic insulator that then couples to the global rotation of the rod so that it's transported in a superfluid-like way, and at the other end is converted into to ordinary magnetic spin. Now, I can imagine that this is very hard, but you know, we need moonshots nowadays. So let me just leave you with this final slide, and thank you for your attention. And I'm happy to take the remaining time to answer questions you may have.
All right. So thank you very much. So let me. Everybody, thanks. You can put out your hand up, but anyway, all it works. Let me have Oliver has a question for you. So Olivier.
Hi, Robert. I don't know if you can hear me.
Yeah, we can hear you.
Thank you for your talk. So I have a question concerning. So in your talk, you don't specify exactly what is the magnetic configuration and if it plays an important role. In particular, what is, does the ellipticity of the magnetic precession plays a role, and can you have in this problem? Do you have is there some efficiency that is linked to the fact that, for example, you have a difference between magnetized in plane and magnetized out of plane? And do you have also issues about the fact that maybe you have a magnetic texture inside the system?
Yeah, let me, thanks, Olivier. So the setup that we consider, indeed, I didn't specify it too much, but the setup that we consider is really the one that's I didn't specify the magnetic configuration. The setup that we consider is really as drawn here. So let's say there's a field really along the axis of propagation. And then these magnets, let's say classically, they precess around this axis. And also the phonons are, let's say, circularly polarized around this axis. So those are the only ones that can transport, at least efficiently transport angular momentum. So I don't think we have not considered explicitly how this would be affected if there would be ellipticity in this precession because of some shape anisotropy, for example. I think this was your first question. Just guessing, my guess would be that there would be some slight decrease in efficiency in coupling circularly polarized magnons to the phonons, but that may be, I'm simply not 100% sure. So that's one answer. The other question you had was about textures. So textures, I don't know. But for example, I could imagine, and again, we have not considered it explicitly, I could imagine that there is some angular dependence if you put one orthogonal to the other. In fact, don't you do something like that in your experiment, that you take put one orthogonal to the other, for example?
Okay, so the configuration so far that we've been considered is a perpendicularly magnetized, where indeed, I mean, the stuff is exactly circularly polarized. Then there is a clear excitation of circularly polarized phonons. But for example, for in plane, there is this issue that, you know, the magnetization then is very elliptical, especially when you try, for example, to do it in a non-local experiment, like you have to have an in-plane magnetic field. And then, in principle, there is the issue of if the phonons that are excited in this case, what are the exact polarization of the phonons that you're exciting, and what is exactly the efficiency of the transfer?
Yeah, so
let's move on to the next questions, and then you guys can maybe discuss afterwards. There's quite a few questions now, if that's okay with you guys.
In any case, thanks, Olivier. Thanks for listening.
Thanks, Olivier.
Thanks for
stick around, and then you can discuss after because there's quite a few. So Simon, you're next, and then I keep track of everybody, so it's okay. Simon, if you can unmute yourself. Simon Heuser, yeah. Ask to unmute, maybe. You have a question, Simon?
Okay, now you can hear me. Yes?
Now, yeah.
Okay, so thank you, Mr. Duine, for the talk. I have a question right to your last slide. If you can go to that, please.
Oh,
summary slide, exactly. Yeah, this slide. Here you wrote that, let's say, the diffusion length of a magnons is limited by the acoustic quality. Maybe you can say a little bit more details about that. And also regarding that, I wanted to know why is or what kind of mechanisms limit this diffusion length of the phonons. Can you consider that also the magnons limitate this diffusion length, or is it, let's say, not that important because of this, you showed at one slide the dispersion relation, and there's only, let's say, a narrow window where this conversion takes place. So can you a little bit comment on the diffusion length of the phonons?
Yeah, so this is a good question. So in our theory, say, let's say that there are, so we put the, let's say, quote unquote, the usual magnetoelastic coupling in our theory. So already via this coupling, you get magnetic relaxation. So that's one thing. And so already you have, so you basically already have any process that would, for example, lead to magnons leaking away in the phonon system or vice versa, you would already have there. The phonon, so the phonon decay, we have not explicitly considered any microscopic process for that. So that it's known from experiments what that is. Actually, also from I think we took the number from Olivier's experiments, and we just put it in as a phenomenological parameter. Now, I could imagine that, for example, there are various processes where phonons decay into other phonons because they need not be conserved. That number doesn't have, etc. But I don't. So at least in our theory, we don't explicitly model that.
Okay. So and what about exactly now about this acoustic quality? What?
Yeah, I didn't understand. I didn't understand your question completely. So
I mean, what do you mean by acoustic quality of the sample? I
basically mean the phonon, let's say the phonon quality factor, the phonon decay.
Okay, that is a synonym for that. Okay.
Yeah. Okay, so let me move on to Matthias. You have a next question.
Yeah, so actually, thanks, Rembert. I really had an interesting observation about the Einstein-de Haas effect and that the scaling of the angular momentum and the energy is different. Now, for large samples, there's no problem because you have too little energy in the rotation, so it just goes into heating of the sample. But if you go to a very small sample, you have the opposite, in that you have too much energy in the rotation. What happens then? Or is this not physical because it's less than one atom or something?
Yeah, so that's a very good question, Matthias. But basically, we have not considered that. So I think it becomes probably less, first of all, it becomes less universal. So let's say the theory we formulate in our paper until at some point is still applicable also to small systems, but at some point we start considering large systems just to be able to do something, so to say. Okay. So I think it's in my opinion a little bit of an open question, or at least there's a lot of work to be done to understand for small systems.
I really like this idea because now I always tell the students that magnetism has angular momentum by the Einstein-de Haas effect, but I never tell them that it doesn't really work with energy and angular momentum, that both can be conserved together, so that you have to somewhere transfer the energy somewhere else.
Yeah, it's really a nice argument. It's due to, let me again say, it's due to Simon Stripe, and I think it shows you that something funny happens as you make or something interesting should happen if you make systems smaller.
Okay, great. Thanks, Sam.
I think just more work to be done there. Thanks.
So the next question is from Philip. Philip, go ahead and get your question.
Can you hear me?
Yeah.
Yes.
Great. So thanks for that very inspiring talk. I would have some questions concerning the first part. So where you were talking about the parallel pumping process.
That's this one.
I think yes, this one. So what kind of system did you consider? Because did you consider Siemens energy for the parallel pumping?
Yeah, it's a very good question. The answer is not really. So what we did is the following. We assume, so we model the parallel pumping already, let's say a few steps ahead after the actual parallel pumping. So we assume that what parallel pumping does is that it injects energy and spin into the magnetic system only. And so as an initial condition, and then we assume that this energy and spin equilibrates, or at least quasi-equilibrates quickly, and leads to a temperature change in the magnetic system and a spin accumulation in the magnetic system. So as an initial condition, we put the temperature of the magnons, this blue curve here, we put the temperature of the magnons to be larger initially, and we put the spin accumulation of the magnons to be larger as an initial condition, and then we let the system evolve, because to actually model the entire parallel pumping process, that's a little bit too complicated, I would say, to just get some. So basically this was just done to show that there can be some interesting non-trivial dynamics, but not necessarily to model specifically parallel pumping. I don't think this is too far away from the truth, though, because parallel pumping, with parallel pumping you achieve Bose-Einstein condensation, so it's not unreasonable to think that it does something like injecting energy and injecting spin into the magnetic system.
But one question I have there is the Zeeman-induced, so Zeeman energy-induced parallel pumping only works for systems which don't have rotational symmetry, so which have an elliptic precessional cone. And our explanation why you can principally translate one single microwave photon into two magnons was always that, okay, angular momentum conservation is somehow not given in this process.
Yeah, but if you include the lattice, there is angular momentum conservation. So I
exactly.
think, yeah.
So principally, this is the thing which is behind, because when you would use magnetoelastic pumping, you can also pump into a system which has a perfect rotational symmetry. But this is not done here.
No.
Okay, thanks.
Are there more questions, Jairo? I don't hear you anymore.
Yes. Can you hear me?
Oh, yeah, sorry.
Okay, so Jairo was muted, but I think I'm the next.
Yeah, sorry. Oh, that's right. I was actually calling. That's my problem. Yeah.
Okay, so thank you very much for this talk. I think I have a rather similar question to Philip's, but before this, here you showed the case when you excite the system with a laser, yes?
This one, yes.
This one, yes. And you said the initial condition is that the laser pulse heats the phonon system.
Yeah, that's at least what we assume, yes.
Yes. I would rather assume that the laser always heats the electrons first. Do you have any reason to assume that the electrons are not heated, or do you think it is not important here?
So that's a good question. So I think, so this is, we're really considering magnetic insulators. So somehow there are not, at least not itinerant electrons whatsoever. So maybe you can, so somehow I would think that any heat, even if it's absorbed really by the charge, it should go to the lattice. And that's why we assume that the phonon system is heated. I don't know if that answers your question, but
and a bit. So we usually assume laser heating, and the laser does not couple to the phonons. So I don't know if you can heat the phonons directly without heating electrons, even if you have an insulator. And if you have to go through the electrons with the energy and then heat the phonons, that's quite okay on the microsecond time scale. But then it could be that the heated electrons directly couple to the magnons.
I see. Yeah, so indeed, so it's thanks for the point. So again, we kind of, as I said, we don't consider that, we just put it as an initial condition. So this would, what you say, would involve really going through the motions of actually calculating how, let's say, putting the heating in the electronic system and then seeing what gets heated first, etc. But okay, thanks.
Okay, if that's an open question, I'm happy.
Yeah.
Martin, you have a question? Martin Schliemann, go ahead and unmute yourself.
Yes, it goes in the same direction. It's just the time scale. Of course, it's clear when there would be metals, then the most important part would be electrons, not the phonons or the magnons, where the energy goes. But even in the electric material, we are here in the microsecond region, which is for me a little bit astonishing. Magnetization, even in insulating materials, the dynamics is faster. And the second question that is a little bit related. For you just calculate everything is thermalized, but you can heat the magnon system on two ways. Either you increase the number of magnons or you increase the energy of each magnon. So why should be everything thermalized? And why it takes microseconds? Dynamics is faster in general.
Right, so I think, so the reason why the dynamics is relatively slow is because we are also doing this. I did not, so of course there are a lot of parameters going into this setup, but we're also doing this at rather low temperatures. So all the, if I remember correctly, maybe 10 Kelvin or so, maybe even smaller. And then we're putting the system out of equilibrium with, let's say, fractions of kelvins compared to this low temperature already.
Okay.
And so at these low temperatures, the dynamics will be slower than the usual what you have in ultra-fast magnetization dynamics time scales. The reason for doing this is just because it's a, let's say, our theory eventually is applicable in some low temperature regime in the very end, let's say, after making various approximations. So just to be consistent with that, we take parameters that at least are consistent with those approximations. Even though these type of curves look, of course, very much like what you see in for example, 3 temperature type modeling of things. Now, let's say your other question. Can you repeat the other question?
The other was, everything is thermalized. You have no hot phonons. Why should you create directly a thermalized phonon system? Or why are the magnons thermalized and not hot magnons or something like that?
Yeah, so this could very well be. In principle, our paper has like full Boltzmann equations on everything. What we do is actually this calculation is just a linear response calculation out of slight equilibrium. So in that sense, these are perturbations around some equilibrium state. Again, just for internal theoretical consistency. In practice, I think depending on what you do experimentally, you have to rethink whether things are really in quasi-equilibrium fast enough. For example, at room temperature, the magnons may very well be because of strong exchange interaction. At these low temperatures, I'm not so sure, etc. So I think that seems to be all my answers about this part. These are very valid points, but somehow, if we would consider them, our paper would become endless. So I think...
No, that's clear. I missed this 10 Kelvin, which is important. You just cool the phonon system down so that the transfer is slow. Yeah, exactly. Now I understand it.
Yeah, so, I think I didn't mention it. So in my opinion, these are...
You did.
Oh, okay, anyway.
Okay.
Don't work. I think you have a question next.
Yeah, thank you. Thanks for a very nice talk. The question I have is actually how does the physical picture change if we have electron in the metallic system? Do you think the phonon spin transport is also important in metallic systems?
You mean in the second half of the talk, for example, in this setup?
Yeah, for example, what happens if the spacer layer in the middle is metallic sample?
Yeah, so I think so this is not backed up by a proper calculation. My naive expectation would be that because the mediation of angular momentum from magnons to phonons at the interface is due to exchange interaction, it might short circuit the phonon path. But again, this would have to be calculated. So it would depend on there are now 2 competing processes, either the phonon channel or the electron channel, and you would have to compare, let's say, resistances of these channels. And since the since exchange interaction at interface between magnets and the non-magnet may be stronger than magnetoelastic interaction, it may actually short circuit the phonon path. But again, this is naive expectation, would have to be backed up by a proper calculation at some point. Does this answer the question? Or?
Yeah. Thank you. I see what you are thinking in this direction. Thank you.
Thank you.
The Oksana, if you unmute yourself, you can maybe ask the question. We don't hear you yet. Let me see, Oksana. Can you talk, Oksana? You're now muted. You should be able to talk if it's possible. We don't hear your. Okay, maybe unfortunately we don't hear you, but may I read the question for you maybe while you work on the technical issues? So Oksana writes here, you mentioned in the last part that your equations are stochastic. Does it mean that you have temperature effects? Wouldn't the temperature destroy phonon polarization? I think I know that, but that's okay. Go ahead.
Eventually it does. Thanks for the question. Eventually it does, but because of this quasi-equilibrium situation, or where you drive the system, so the spin is really injected into the phonon system and eventually decays. But this decay length is rather long. To put it in a more technical language, we have a let's say a damping parameter, which is governed by well, where the input is the acoustic quality. However, the fluctuations via the fluctuation dissipation theory are proportional to this. So these kind of effects go hand in hand, and weak damping just simply means that it takes a long time, but also in a length scale language, it takes a long length scale until the phonon spin decays. And so this decay would be due to, let's say, disappearance of the phonon spin as you make the system longer. So yes, you're right, but all spin disappears eventually because spin is not conserved. It just depends on how slow it goes. Yeah. Thanks.
Okay. Then Yang Yu Zhang, go ahead if you can. Go ahead.
Yeah, can you hear me?
Yes.
Yeah. Thank you for your interesting talk. I just get one question about the setup structure. Yeah, in the last several slides. Yeah, the structure is magnet, non-magnet, magnet. Here, this structure for me, it looks quite similar with spin valve or magneto tunneling junction, but the phonon the transport range for phonon is much larger than others. So, but I wonder, does they share some similarities in the transport properties? Yeah, with yeah.
I understand your question. Indeed, it looks very similar. I think what is shared, for example, are things like if you compare magnitudes of spin current as a function of angle between these two magnets, or if you compare parallel and anti-parallel, you may find that they differ and some magnetoresistive type effects, etc. So I think in this aspect, they probably share some phenomenology. However, in terms of theoretical description, length scales, physical processes, it's of course very different.
Yeah. But the scale of the phono devices should be much larger than spin valve or MTGs, right?
Yeah. So it should be much larger. So the only thing which I think is similar is somehow just in terms of like angle dependencies of the spin current, for example. It's probably very similar to an angle dependence of the charge current that you have in a tunneling or GMR device or so.
I see. Okay,
yeah.
Thank you.
The next question I'm going to ask is the person, Dimitro Bosco, had to go to teach, but wants to hear the answer online later. He will check it out. How does this proposed experiment differs from the case of magnetic domain walls, where the magnetic moment is also twisted, thus affecting the lattice? I have that's the question, and then he would like to get your answer.
Right. So I don't fully understand the question, but I think at least in the case of a twisted magnetic, so I think what he means is that, and you can write me an email later if I'm answering this in the wrong way. So what I think is meant is somehow if you have a domain wall through this system that connects this domain to that domain and how that transfers angular momentum.
Yeah.
Because what is different here is that we have within this magnet magnetoelastic coupling that couples, that excites phonons that then travel from left to right. So you really have a particle conversion process, and which therefore also amends itself to incoherent setups where you drive things thermally. I think for the twisted domain wall type setup, I don't know how the magnon/incoherent generalization of that precisely works. So yeah, that's it for now, my answer, but feel free to approach me later when you're done teaching.
Okay, great. So Amit, to go ahead and unmute yourself if you like, and if you can.
Thank you first for the fantastic talk.
Thank you.
So it's a perhaps a naive or fundamental question. How will this be different if instead of the magnets that you use on both sides, you use non-spin angular momentum? So spin is not, it's only homomorphic to angular momentum, not isomorphic. And there may be a difference if you use, instead of magnets, you use I don't know, photons with spin with photons with angular momentum to transfer through a phononic sandwich in between.
Yeah.
And I think it's a bit, I should intercede a little bit, because I think it's related to the next question by Vladimir Houston, that while longitudinal phonons with non-zero orbital momentum are ignored. This is the, I think it's connected to that. I just wanted to add that in.
Yeah. Yeah, I don't fully, let's say I don't fully understand the question. So at least let me say that so what you're saying is, if we would consider, rather than a reservoir of spin angular momentum, rather than considering this magnet as a reservoir, we imagine that we inject from a photonic system. And then,
for example.
Yeah. So I think first of all,
the question is whether the phonon spin here, whether the spin word is important, or whether you're using the fact that the phonons can transfer angular momentum.
Right. So let me see how to answer this. So in this simplest, let's say, setup, it would be where we just have, let's say, a single. So we just imagine having a single lattice that consists of a single atom, so only one deviation, etc. It would always be just the phonon spin that transports angular momentum. So I think if you look at this more generally, then it could be any, let's say, angular momentum. It could also be orbital angular momentum. And then the second point is that somehow this setup that you have in mind would really be a coherent setup, where you have you imagine converting a single photon spin into, let's say, something carried by the lattice, and then perhaps extract it. So here we were really interested in having a reservoir here, and making a reservoir of photon spin, I think, is much harder. But that's more kind of like the application that we were looking for.
All right.
I think it's a connected question to Vladimir, where he's interested on the orbital one. Yeah.
Do you hear me?
Yeah.
Yes.
Okay. You see, when you introduced the phonon polarization and said that only transverse phonons keep some spin, you see, this is in the frame where which is bound to the phonon, to the direction of phonon momentum. In general, phonons, like photons, may have orbital moment. So the total angular momentum of a phonon or of a photon is summed as the contribution of the polarization and of the orbital structure of the phonon. So why, in this sense, longitudinal phonons may also have angular momentum.
So what is precisely the question? Why, or is it more like a comment?
The question is why longitudinal phonons with non-zero orbital momentum have been ignored in your approach.
Yeah, it's just because we consider very simple systems where this contribution is not there, I think. So I think to have this contribution, you would need to have more involved atoms, let's say, or let's say more involved crystal structures, if I understand it correctly. But in
I don't think it has any relation to crystal structure. You may deal with a continuous system and just with acoustic phonons. That's it.
Well, I don't, at least in our setups that we have, we don't see this, let's say we don't see these contributions popping up. Meaning that if we, it's not that we put in the phonon spin, it just, let's say, comes out of calculating the spin current that goes from left to right. And then we only see the spin contribution going from left to right. So this other contribution simply doesn't pop up there.
I think maybe the comment would be that in this case, this phonon longitudinals with non-zero orbital momentum would average out in his setup. It's not like you can have, of course, something, a surface phonon on one side that will make you twist in the other, but in equilibrium in his setup, they both would be there at that temperature from left and right. So in that sense, it's not in his setup itself. You would have to bias it somehow. If I understand Vladimir's point.
Yeah, that could be.
It could contribute, of course, but it would be more in the global rotation sense. Yeah. If I understand correctly. That's a good point.
Okay, thank you.
Okay. So with that, I think we've exhausted everybody's questions. Janko, you have maybe a last question there, maybe, or comment? Janko Milev, you have your hand raised up. I'm not sure if you're to thank for the talk or. Okay.
I also have to bring my kid. I have to bring my kid to drumming lessons in 5 minutes. So.
Okay. So with that, we'll let you drum away. With Olivier, I guess if you guys want to discuss later, you guys can do that. But
I think Olivier maybe wants to talk, but then we have to make an appointment separately, Olivier, or I can.
Okay. So with that, we thank you again and have a great time. And I hope to see everybody back next week with Stefan Blugold's talk, where he's going to tell us a little more technical aspects of how density functional theory can build chiral quasiparticles, etc. So we're looking forward to that. Thanks, Rembert, and you can play with the Legos for a few minutes before you go. Tell me.
Can I just leave the meeting, by the way, now, or you want?
Yeah, you can leave the meeting anytime.
Because yeah, thanks again.
Thank you.